Can everyone hear me in the back? Yep. Okay. Okay, let's get started, folks. Thank you all for coming. Welcome. My name is Conor Cunningham. I'm an architect on the SQL team. I work on SQL Server right now. However, I also have been working on the SQL Azure product, service, whatever we call it. And this talk is really about a lot of the lessons that we learned building large-scale telemetry systems to run cloud services, including the SQL Azure service, or Microsoft Azure SQL database, which I will call SQL Azure just because it's so much easier to say. So I can tell that all of you are above average and smarter because you came to this talk today. This is the real talk you should have come to. The one yesterday was just for everyone to feel good about themselves, but today is the one where you learn something. Instead of just making your life easier, I'm going to show you how hard some of the problems we're trying to solve are. So please turn off your phones. A little bit about me. I've been at Microsoft for a total of about 17 years. I took a break and went and did startups for a while and then came back. I work remotely for them from Texas. I fly up here every month to Seattle to come work with the team. As I said, I'm an architect. That means a lot of things to different people. For my job, the easiest way to describe it is I work on the core strategy for how do we make various parts of the system work, and I also have to fix all the things that go horribly wrong. So if there's a problem with the system, it's my fault. It doesn't really matter if I did it or not. I have to go figure out some way to make it work. And the neat part about that is I get exposed to all the interesting problems that come up, and they pay me to go fix them. And it is one of the most fun jobs in the world. I can only tell you that I enjoy coming to work every day, pretty much, almost every day. And this talk here is really about some of the stuff that you're going to be seeing in the future over the next couple of years. Even in on-premises situations, these same techniques are actually quite valid. And a lot of the stuff that you're going to learn here is really about how to think about solving problems. So we run a service, and we have more than 1 million databases in this service, and those databases are up every day. And anyone want to guess how many database administrators we have running them? 0. We have 0 database administrators. We have a bunch of highly paid software engineers who are dealing with parts of the system and keeping it working, but we have no database administrators. So there's a bunch of features that come with SQL database. You have HA turned on all the time. You have automatic backups, automatic upgrades, patching, all the different things that you need to do to deal with the regular operations of a system are done automatically in SQL Azure. And the neat part about that is that it lets us focus on design problems and scale problems and a lot of other things as well with our customers. It doesn't mean that there's nothing to do. In fact, we're always adding new features and making the system better rather than just having to worry about, did I finish my backups today? We have about 10 data centers or so around the world, different regions, and customers are spread across those. There's some in Europe, there's some in America, there's some in Japan, there's some, we recently announced some in Australia. We don't have them in every possible region yet, but we do have a fairly deep amount of coverage at this point. And we have lots of different kinds of customers from around the world. Some of them are running local in just their nearest data center, and others are running global applications. A number of first-party Microsoft properties also run on top of SQL Azure. And if you're using parts of Office 365, for example, parts of that run on top of us, and there's a number of other services. The Visual Studio Online service, which is the developer tools portion about how you can check in source code and stuff like that, that all runs on top of SQL Azure as well. And there's a bunch of very, very big projects being run there right now at massive scale. VSO has 2 million plus customers worldwide, and that's growing rapidly. So it's actually pretty important to think about when you get to that scale, there's a few things that are different about what it means to troubleshoot a problem. Today, if you have a single server and that server is misbehaving, hopefully you can kind of sit down, write a few queries, look at a few DMVs, perhaps you look at the error log, And this is a fairly manual process in some respects. But it's possible to do live debugging in many cases on a system that well. There's some big systems where that's difficult, but for the most part, you can kind of go up, look at the system, drink your coffee, ponder how life is going, and then figure out what you're going to do to fix whatever random problem you have on the system. This really starts to fail when you have tens of thousands of machines, and it just doesn't work anymore. You have to think about the problem differently. So a lot of what I'm going to show you today is sort of the evolution of the thought process, about how you go from this first worldview of I can go look at the problem with DMVs or whatever, to how do I make it work without having to necessarily get up in the middle of the night and figure out what happened. Okay, I just did that. Okay, how many people here like Kung Fu movies? I love bad Kung Fu movies. Doesn't matter what they're about, I will watch them. Because someone's father always got killed by some other rival clan, and then they each have different styles of Kung Fu, and one's gonna go fight out against the other, and there's metaphors and all sorts of deep levels to these things. Greatest thing ever. Watch them in the middle of the night. I'm waiting until my daughter is old enough to watch Kung Fu movies with me. And the way that I like to think about Kung Fu movies and how it deals with this problem is, you guys have been doing one style of Kung Fu, like Eagle Claw. And there's another style of Kung Fu, which is also valid, Monkey Fist. None of you have been doing Monkey Fist, and I'm going to teach you Monkey Fist today. And if you think about it a different way, you'll find that you'll be able to take the techniques here and use them no matter what the scale of the problem you're on. Now, obviously, the amount of money and time you might invest will be different based on the scale of your problem, but I'll just tell you that we can only do the techniques at scale that we run here in this deck today, and we can't really go manually look at systems except for stuff that we haven't seen before. And then we have to constantly automate that to be able to keep up with the growth of the system, because there's a lot of you guys and not as many of us. And frankly, the goal is to give you guys a democratized version of a cloud service for databases that does all the things that we want for our platform as a service offering. So the typical model for traditional SQL Server is some customer calls up to the IT department and says, hey, my app's broken. The DBA might go take a look at what's happening on the machine. Maybe you need to get the machine admin if it's someone else. Maybe you have to go talk to the SAN admin if you've got a SAN. And you eventually start looking at various telemetry encounters that are there. And you say, okay, here's the problem. Maybe I need to go change this query. Maybe I need to reboot the box. Maybe I need to clean out the transaction log by doing a backup. Any of those things might be an operation that you'd see today in any shop around the world. This model assumes that whatever it is that's going wrong can wait until the expert is available to take a look at it. It assumes that you don't get overwhelmed with too many issues at the same time. And it assumes that whatever you've built is understandable enough by whatever that expert is to be able to make the right mitigation call, hopefully during business hours. In the cloud, most of these assumptions prove false. You're usually running 24/7 services. Usually they're distributed around the world, which almost guarantees that 2/3 of the time, the expert that you have in one region of the world is not going to be during their working hours whenever that problem happens. And things tend to fail when you least expect it, and you often aren't planning to deal with whatever the issue is. And even if it did, the system is complicated enough that you might not even know what's wrong. So these techniques we've been using on-prem don't tend to work as well in a cloud environment. And as a result, we need to rethink how to attack this problem. So instead, the idea is move from a model where a human will go and interact with the machine as the first way of debugging to a model where you're emitting the right kind of telemetry out. And you're constantly able to watch that telemetry and figure out, what do I do with that, hopefully in an automated fashion, to find issues and resolve issues more and more automatically over time. The typical way that we talk about these in cloud-facing apps, because not everyone here probably has built one, is usually you have some sort of SLA. Your department that runs the database system might have an SLA for how you run your on-premises environment, but that might not always be true depending on the size of your shop or what kind of work you're in. But we will have SLAs. For example, in SQL Azure, the uptime SLA is 4 nines, which means 99.99% of the time, uptime SLA. And an SLA is a service level agreement. It doesn't mean that we always meet that, but it is a target that we most of the time meet. And we will meet that for a very, very large percentage of our customers. And we actually measure that every single day and look at that number. And we do work to make that number go better. So it takes a lot of work to meet an SLA at scale. And we have a whole pile of people that work just on that problem. So at larger scale, you typically also have ISVs. And ISVs will have their own customers on top of it. And the thing that's also interesting about this model is, whereas in a traditional ISV, you would buy a copy of SQL Server, and you put it on a box, you buy a copy of their application, put it on an out tier box next to it, and you'd run it. And that's the scale. You can buy a big box, whatever, but that's the scale that you run. In these cloud services, there's typically a couple of databases, and they're shared across many customers, and there's all of the customers in one place, like going through the app tier and sometimes through the data tier at a time. So that means the scale that you typically see of these is far, far bigger than what you're used to. Right? I mentioned VSO has 2 million accounts, and they're constantly running machines at almost full capacity to figure out how to squeeze out the cost to the system and optimize that, their use of the hardware. And they've run in lots of different stamps around the world, and they're running many, many premium databases to make that happen. So if I have too many machines, then I can't go log into each one. And I also want to figure out, how do I solve problems as quickly as possible? The typical pattern for most of us would be, we want to understand what's wrong and then figure out how to fix it. The challenge is that that often means that you spend a lot of time doing root cause analysis while the site's down instead of doing mitigation work. So there's actually a key principle here, which is that you have to separate the work to mitigate from the work to do root cause analysis. Often, you can really quickly mitigate problems. I used to have an Apple II computer back in the day. How many people are as old as I am? Okay, so I loved playing games on this thing, but sometimes it would just not work. And the actual best thing you could do when it stopped working was hit it as hard as you could. And the reason is, it used to have all the chips, and they would not necessarily be seated correctly. And if you hit it, sometimes it would knock them just a little bit, and the machine would start working again. It was the greatest thing ever. I really wish servers these days still had a hit it option. I mean, think about it. It would be so much more fun. Anyway, the challenge is that if you really want to figure out exactly what's wrong, you're going to spend all day taking chips out and putting them back in and rebooting the machine and trying stuff. And that's not what you have to do when you're supposed to be up the whole time. What you need to do is figure out, how do I make it so that I can make the system work, at least pretty well, until I can figure out exactly what's wrong. So offline, during business hours, hopefully, you can look at the telemetry and figure out, oh, what actually happened was we ran out of memory, and then we started spilling to disk, and then the system got slow, and all of a sudden, queries started timing out. You should be able to figure all that out from telemetry instead of just trying to look at the system when that particular issue is happening. It may be that you couldn't even look at the system while it's happening if you had just a regular DMV approach, and that would cause all sorts of issues if you just don't figure it out, because your customers might have already left by then. So cloud services have this different approach because there's a different set of expectations, and ultimately the scale and those expectations combined need you to have to try a different approach. Monkey fist. So ultimately, when we go figure out issues today with the service, we'll have a whole set of troubleshooting guides, and those troubleshooting guides are focused on mitigate before they figure out root cause analysis. And if we have a problem where we don't know what the root cause was, sometimes we don't figure it out. We'll add more telemetry in so that next time we can figure it out. So if we didn't have enough information to tell that we were out of memory at the time, we'll add another performance counter in, or we'll add some telemetry that emits certain things when we're low on memory so that we can see that condition ahead of time. The challenge in one of these big services is, once you get to a certain scale, your customers know that their clicks on your website are failing, but you might not know that. A lot of services that start off, they don't have any telemetry whatsoever, and they just have angry customers starting on Twitter or whatever, and ultimately they just can't figure out what's wrong because they don't have telemetry, and the customers just leave. And often you just have customers leaving your service without you even knowing it. So you have to monitor so that you can find those customer issues before the customer does, and hopefully fix them before the customer does. So I measure how we're doing in the SQL Azure service based on how many times a customer finds an issue before we find the issue. And for a while back at the very beginning, we had a partner team, and they were finding issues all the time, and I got called by their executive guy every single time, and it was really annoying to get called by a senior executive at Microsoft because it was more than just a friendly call. Right? Anytime a technical fellow at Microsoft calls you and wants to talk about your service, that's typically a pretty bad sign. And so I got these phone calls, and I was on a first-name basis with him, and it was great fun chatting with him. I learned a lot, but it was not a courtesy call. So we had to go figure out how to fix the SQL Azure service and add more telemetry, and now we're at the point where I have our team finding issues before their team finds the issues. We're telling them about those, and that means that we've gotten to the point where we're mostly able to find the issues before they do, and I feel a lot better about that. And I'll show you some of the techniques later in this deck that we use to make that happen. I want to talk a little bit about taxonomy. Whenever you start building large services like this, there's a challenge for, hey, I want to go find whether the site's down, which is kind of an alerting scenario, versus whether I want to do an investigation as to what's the model for how often people choose to buy extra features in my service, to what's the daily report on how are we doing on our SLAs. Each of these are different types of telemetry and different kinds of requirements on each of them. And they often are segregated out by data size and time horizon. So alerting, you want to know data right now. You want to have just enough information right now to make that happen, but you don't really want to have terabytes and terabytes of data you have to go through because it just takes too long. You want to know, is the website down? And you want to have a Boolean on that. Every 5 minutes, you might go check with a ping to see if the site's up or down. And that kind of alerting is very simple to build, but it's different in terms of the expectation for how long you can take to figure that out. If you find out only after 3 hours, that's no good. You have to find out really, really quickly because otherwise your customers have already left. Now, dashboards and reports are kind of more in the current time. You might have a lot of data. You might be able to look at it every 5 minutes or every hour or every day. And depending on how much you want to do there's different techniques that you can use. Often you can run queries against a database, or you can use certain kinds of services that we have in the Azure ecosystem to let you collect data and give you summary information on particular granularity to help you figure out, hey, am I adding customers in my service? Are they buying things from my website? Or whatever it is that you're in the business of doing. The data science one's actually kind of nice because often what you want to do is look at all the data over all time. Like show me a model for how often people use physical I/O based on database size. And you go build a model, and then all of a sudden you can predict what should the next generation of our hardware look like based on all the telemetry that you've collected for all time. And you want to keep that data so you can make a really cool decision on that. But it's also really hard if you only have 500 gigabytes in your Azure databases. You can't put all of that in one place. So you have to get really creative about how do you collect and store that. And then also, how long does it take you to run a query on top of that data? Any questions on this? Okay, straightforward. So I'll tell you a little story. I had originally done a version of this talk as part of an all-day pre-con that we would do with the Azure Cat team. And the idea was to introduce people to how SQL Azure worked. And this was one of the segments on how telemetry worked. And I gave a version of this talk when I was in Dublin in September. And sadly, my partner and I looked at all 4 of our talks. We had 4 90-minute decks. And we got about 2 weeks before this, and we looked at them, and they were completely out of date. We had done them a year before, and all the technology had changed. So I'm telling you about this right now, not because I expect that every single thing in this deck is going to stay current forever, but the ideas in this deck are actually the thing I want you to take away. But understand that it's evolving so rapidly that the techniques that I had to use 12 months ago are actually not the techniques I would recommend today, because there are now new services available and new techniques available that make it so that it's so much more effective to try the new things versus what would have been best state-of-the-art before. That's a very exciting thing. It means the space evolving a lot more rapidly than a traditional SQL Server environment. And I think that if you go for the next 12 or 24 months, it's going to be evolving very, very rapidly. There's no custom box product thing that you can just go buy that solves this problem today. But there are some techniques that get close. And probably over time, there will be more turnkey solutions that come up. So the people who are doing this right now are highly motivated, and they also don't really have any other choice except to write their own. Did I say everything on the deck? Yes. Okay, so I'm going to go through about 3 different checkpoints on the different kinds of techniques that people have used to figure out how to make this service thing work. And the telemetry model that goes through there will start off with what a traditional SQL Server person would probably try to do if they were to build such a service first. I'll start out with the zero-click stuff, actually, for this room that's even more SQL Server specific. And then we'll work our way up to ever more exotic techniques that we use to run services at scale today. So first thing you do if you're a traditional on-premises SQL customer and you want to do logging is, we all like databases, right? So we create a database and we put all the logging records in the database. And that works for a while until you have a lot of telemetry. And then you realize, wait a minute, putting this in the same set of physical hardware as my production system eventually steals all the I/O from my regular production system. And then the boss comes and yells at you, and that's no good. So then the next thing you do in the cloud world is say, wait a minute, Azure storage is really, really cheap. And it also has more IOPS than a traditional SQL Azure database. But it doesn't have exactly the same kinds of transactional guarantees. But for logs, that might be OK, because I only write it once, and then I just want to read it later. I don't really need to update it like I do a traditional banking application or something that I might put on a database. So I can take logging data, and as long as I can get it out into Windows Azure storage, like table storage or blob storage, then I can write a lot of data there. And you can store stuff. It's very, very cheap. It's something on the order of 3 cents a gigabyte per month for geo-replicated storage. I think it might be 5 cents for geo-replicated. But it's very, very cheap relative to the cost to expand your SAN, as an example. So then you start writing stuff out there, and you're like, this is great. I can go put stuff in there. And then you try to read it, and you're like, well, how do I read a petabyte of whatever I've written out to blob storage? And you then realize, well, the database can't do it for me. I have to go build something, or I have to use HD Insight, which is a Hadoop cluster technology, or some other thing like that. And it's often a mindset shift from someone who's traditionally a SQL Server person to go jump into that technology. They're not the easiest things to pick up. They are very powerful, though. And in many ways, they're complementary technologies to what traditional, especially OLTP databases do in the SQL world. So the challenge that I'd like to explain to you is it boils down to 2 different things. If you want to look at lots and lots of data, it's going to take you longer to go through that data and get it to a point where you can get some value out of it. So often, alerting needs to have a smaller amount of data, and you can use different techniques than the larger things in the space that we saw for that taxonomy slide. And that means that if you want to do data science or daily reporting, those technologies need to be a little different, and the latency expectations that you're going to have are going to be higher. So bigger data means greater latency at the most simple form. And over time, hopefully that will get better, but nothing I've seen shows me that it's ever going to be immediate if you're going to try to query a petabyte of data. That becomes a very, very big distributed systems problem and quite nasty. So when you start building services, you might then split into 2 pipes, fast pipe and the batch pipe. Fast pipe is for alerts, batch pipe is for everything else. That's what most of the big services do these days. Let's talk about what kind of data you would typically collect. A lot of this is the same kind of stuff that you would see in a regular SQL Server environment, like an enterprise SQL Server. You would have perf counters. You might be looking at those. ETW events is very common for the app tiers especially. X events if you're in SQL. DMVs if you're in SQL. Sometimes the information really isn't available in X events in a way that's effective. In other cases, you might have other tracing that you might do on your own where your application emits out whatever you want. So typically, you start off and say, I don't really know what I need to put out there, so you'll just try something, and then you'll realize the next day why it's not any good, and then you'll change it, and you'll keep deploying versions of this until you get it right, or until it improves enough. And you're constantly tweaking with this. We're actually, even today, I was having a mail thread with some people on additional X events that we have to add into the service so we can figure out what's going wrong with one of the things that we're seeing when we run the SQL Azure service. And this is a constant thing. Every day it's something different, and hopefully it's different because you're not having to fix the same problem over and over again, but it's actually because you're having to figure out how do I automate that. Okay, so for batch pipes, we're going to talk about a couple of different techniques. These are the techniques that people typically go through for how they think about it, especially if they're moving from an on-premises world to a world where they're mostly cloud-centric. This is not really about the cloud, though. This is really more about the techniques you can use. It so happens that the people doing this first are doing it in the cloud, but these same techniques work on-prem. If you wanted to go buy a large amount of storage and do the same things, we have customers with the same basic technology running in on-premises environments. So the first technique is going to be logging to table storage and using SCOM. Second technique is going to be more of a blob storage plus SQL database hybrid model. And then third is in the big data space. And they get ever bigger in scale and ever more exotic for a regular SQL Server customer. But you'll understand why we ordered them this way, because this is typically what people try to do when they're learning how to build these. Can you guys see the screen okay? Did I do the zoom? I can zoom it in if you want to see. Let me know in the back if you can't see. So first approach is Windows Azure Table Storage. How many people are aware of table storage? Table storage is a NoSQL-based tabular store written in Windows Azure Storage, which effectively is like a combination between a file system and a blob store. It's very, very good at handling basic stuff, but it doesn't have the full SQL Server type system. It doesn't have all the data types. It doesn't support transactions. It's not really a traditional relational store, although you can store some tabular data in it. So people will start trying to write stuff into table storage, and SCOM has a thing that goes and reads from table storage, and ultimately the SCOM has a management pack you can install, and it'll go pull information from table storage. And that'll work for a while, and you can see information in your SCOM management, your on-premise management environment, just like you're used to for many people who use SCOM. How many people have used SCOM before? At least aware of it? Okay. So it's nice in the sense that you can leverage your existing skills on premises, but it doesn't necessarily scale as much as necessary. So table storage will eventually top out. There's a certain number of transactions per second that you can do against that before it starts throttling you, because the technology, just like any piece of hardware, they give you an SLA on what they give you out of table storage, and the SLA for that is actually modest when it gets down to it. You might get 5,000 writes a second, something like that. And once your service gets big enough, you have lots of different nodes in your application tier, many databases, you start hitting the limits of that really, really quickly, especially for a global cloud service. There's a management pack. It's not been revved in a while, but I put a link here just so you can go see this. So if you wanted to try to replicate this for anyone who has an on-premises SCOM environment, it's there. And just go look for Azure Management Pack for SCOM on Bing, because we don't like Google, and you can go see whatever's there. So in terms of how that technology works, you can use table storage. 1,000 entities per partition per table. See, I had it wrong, not 5,000. I apologize. You can put performance counters in there, but you have to use partition. You have to partition things using the right key to make sure that you're constantly balancing the load. And eventually, you get to the point where you're just really having to spend your whole day trying to figure out how not to get throttled by Windows Azure Storage as you go down this path. When you consume the technology, the same thing applies for reads. You're throttled on a different level for a number of reads, and this can be a different point where you get killed. Now, once you get to the point where you can't scale anymore because of the table storage count, then you can decide to change the grain of what you're collecting. You can say 5 minutes of data aggregated together instead of 1 minute of data, and so you only write every once in a while instead of every single event that you have. You can skip out less important events and try to optimize that, and we've seen people try to do that for a while. And as long as you keep things within that scale, this might be a great solution and work wonderfully for you. So I don't mean for you to take away that this is not any good. This is actually perfectly fine as long as you're willing and able to live within the restrictions of what that can do. The problem that you've got with this is often the amount of data that you want, especially in PaaS services like SQL Azure. We don't expose performance counters from the machine because that's not what the PaaS service does. There's often many customers on the same machine, and as a result, exposing information about those performance counters may not make sense to you because you'll just get information about what other people are doing on your machine, which doesn't help you much anyway. In the IaaS approach, if you're running SQL Server in a VM, you would be able to obviously get the performance counters out if you want. And in an on-premise environment, you'd also be able to do the same thing since you would own the machines. Okay, so let's go to the next model that people try. They realize, you know what, I need DMV data, and I need more performance counters for my databases, so I'm going to start pulling things in addition to capturing information the way I was doing it from my application tier. So the application tier might move to blob storage instead of using table storage. You can do more stuff in blob storage. It has a higher write rate because you're often grouping things together before you write them, and it's more efficient to write the blobs than to write into the table storage implementation that they have. And then you're trying to use some sort of worker role that's running a VM that pulls your databases to get out common DMV, DMV exec query stats and this and that because you don't have the query store to help you solve problems here. So this is the next technique that people try, and it works again up to a particular point, but you're going to find that it also fails to scale because either you run out of time collecting information from the worker role, or the place you store the output of that, like a database in this case, might run out of write throughput. The other thing that's interesting about this is people start figuring out how to build dashboards to kind of get a view of what's going on in their service. It's kind of like the perf counter view you see today, but more complete, and it actually has more information that helps you understand what's happening at each tier of your service. Here's an example of one of the dashboards that we used a while back, and you can see, probably, maybe not, it's a little bit small, let me try. So we would have processor time, and you could see how many cores were running on this particular thing. And you could see, oh, here's the execution time for this was a web page, website, and at one point we had a spike there. That was not good, so they were working on why did it take a minute to return pages back. That's obviously not what you want. And then you can see here how many users were online and how many requests per second. And then you wanted to figure out the exact cores and query exact, correlate information that's common for why this website would work well or not. and then figure out how many reads and writes are happening in the database. And you're constantly trying to figure out how to tune these things, and if you have a spike for some reason, someone checked in a bug and it's writing too much telemetry, then you can go find that really quickly, hopefully, using the telemetry dashboard, and then hunt back to, okay, now how do I make sure I have exactly the right data to make decisions on my big service? So this is the next level of nirvana that you achieve when you're trying to figure out how to run one of these services. And you can use a lot of the same techniques that you would think about. You're writing a piece of code that goes and pulls DMVs, and then you insert them into a database, and then you run some reports on top of that. Maybe you can even use reporting services if you've got that hanging around. So that's the sort of stuff that you would do. This would also, I assume, be normal enough for an average SQL Server person. In fact, there's actually a piece of code that you can go download that does an implementation of this. It's called the Cloud Service Fundamentals. And there's some links here, but you just go search for it, you can find it. And it's effectively a sample implementation of the techniques that we saw in Approach 2. So it'll go have a little program that pulls DMVs, puts them in a database, and does a report for them. This is done by the CAT team, the Azure CAT team. And I worked with them on pieces of this. So blob storage is better than table storage in the sense that you can write more stuff to it. You'll hit the limit later on a particular single storage account. However, if you start thinking about how you generate the telemetry, you have to do the DMV polling stuff, which has got its own set of limitations. Often, if you're polling DMExec query stats, DMExec query plan, you have to figure out, what did I see last time? Do I want to write all of it each time, or just do the diff and write the net delta? That takes a while to go right. That's one of the reasons, again, we put the query store in place, so hopefully that'll become easier for you over time. You can do multiple threads on the worker role. You can have multiple worker roles, and you can scale that thing to a point. But ultimately, you're going to reach the limit of whatever one of those pieces can do when you're trying to build this system. And most of the time, it's going to be the Azure SQL database that you're storing that telemetry in, or the IaaS VM storing telemetry. You can get a certain size and a certain number of IOPS in those things, but it's hard to make that thing work as an all-up data warehouse with the technologies that are there right now. There's just too many hiccups that happen to make, in terms of the normal experience that you'd have versus hardware you might run on premises. You often can buy a massive storage array. You can have an HA copy of the machine. There's a lot of things it can do, but you have to be willing to accept that during peak times, sometimes the Windows Azure storage account might move you to another node, and that might take 10 seconds, and you might not be able to write it all for 10 seconds. And this sort of thing is not as common in traditional dedicated hardware that you'd see, especially in tier 1 environments on premises. So telemetry, you have to be a little bit careful how you read and write it, but you can get a lot of the same kind of information and write it into a database and make a lot of progress on getting the information into a form on which you can report. The basic scale limits are fundamentally, though, roughly the same as the first one. It goes a little bit higher in terms of the constant factor, but you're going to get to the point where at some point your service is too big and you can't write to the database anymore, and then you want to get the data faster, or you want to do more data than what you've been able to do with this technique. A lot of the Microsoft services got to this point a few years ago and started working on other technologies at that point. So this picture is a portion of what we do in Azure SQL Database. And I should clarify that we're constantly changing and improving the Azure SQL Database telemetry model. So there's parts of it that are actually not like this anymore exactly, but this is sort of a good representative model of what you could do today. Not necessarily exactly what we're doing, because sometimes we have technologies that we're asked to go try out and develop before we bring them to market. So this is the next click stop along the way. And when I made this deck, this was, and it still is, a portion about how we run our telemetry service. And there's other parts that we're working on which are not like this exactly, since we've taken ideas from this and we're working on the next click stop, but I can't talk about those in the deck today because we haven't finished them. But the technologies here you can do on your own. And these services are public today. So I'll talk about this because I think it's more actionable to have that than an exact representation that I'm not allowed to present in a public forum anyway. So the Azure SQL Database Service has 10 plus regions. We have many, many clusters, which is a group of machines that we have sometimes multiple clusters per region. We don't talk about clusters with customers. They're transparent to you guys, but they're our unit of purchase, and they're usually 10 or 20 racks, something like that, of machines. And we'll generate about 15 or so terabytes of telemetry per day across all of the different clusters that are there. We store them all in Windows Azure Storage because it's relatively cheap, and we have many different storage accounts around the world so that we can get a very, very high write rate. We also have a large middle section here in the deck, which is, I'll zoom in on so you guys can see real quick. We're running HD Insight, and we're running pig jobs and hive jobs on top of that to be able to run basically MapReduce or technologies to say, you know what, I want to aggregate all this data to show me information per hour, and that information gets run across a very large set of machines that we've been able to get into our HD Insight cluster. We currently run that in one region, although there's nothing stopping you from doing it in a bunch of different regions. Once we get done with that, it generates a bunch of additional files in Windows Azure Storage. You can see that here. And we also have a queue where we mark off that various parts of our system are done. For example, we'll process the information about how many people were able to log in successfully. And we'll have a job which is constantly running, which keeps track of all of the login failures that happen across all the users in the whole service. And we'll write that information out, write some special jobs which go process and aggregate that. And then we put the results out in Windows Azure Storage, and then we import that using an ETL process into a data warehouse that we currently run on premises. That data warehouse is something on the order of 10 terabytes. It changes depending on what we're doing. And this is running 24/7 every day. So we have a whole lot of these. They end up being fact tables, and we have a set of dimensions. So we have a dimension for databases, and we have a dimension for clusters, and we have a dimension for all sorts of different things you do with standard data warehouse techniques. And then each of the data streams that we're collecting ends up being fact tables, and the aggregation that we do is the grain of those fact tables. And we use all the stuff that we have in SQL Server 2014 and beyond to do clustered column stores and partitioning, and we have an automatic rotation policy so that old data after a few months gets rotated out, and then the new data gets a new partition, and you go insert the new data into a column store right away. And it works out pretty well for generating a bunch of reports. We run our whole business on this, and I get tons and tons of mail every day that reports off of all the different stuff that we've generated. We probably have, I don't know, 50, 100 reports that we run off of this, and we're doing this at scale 24/7. So we might run reports on a daily basis for some things, maybe sometimes weekly for other things, but overall, we're just constantly pumping this data in because somewhere, someone in the world is able to log into their database, and we want to have a report for that. Are there any questions on what we've seen here so far? It's not as easy as it sounds. I will tell you that building such a system is actually quite hard. The scheduling pieces are probably the challenging bit here. Getting it to set up and run and actually make sure that you can detect whenever your telemetry system has stopped working for some reason is actually the biggest challenge here, because you have to build yet another external system with telemetry that doesn't go through the telemetry system to tell you that your telemetry system is not working. Yeah, what's the delay that you usually see for this system? So let me clarify before we go further. What I'm talking about here is the batch pipeline, not the fast pipeline, right? So for this kind of data, we typically aggregate. We have jobs that run every hour. And so the latency will be between 1 and 2 hours. One of that is the wait to get enough data to run a job. And then depending on how busy the system is, it might take 5 minutes to run the job. It might take an hour to finish the job. And it really just depends on how many jobs we have in the system and how we've tuned them. So we might be running 100 different workflows at a time, times however many clusters that we have. So it might be that we're running 500 different jobs, and if we don't schedule them quite right or they're not tuned correctly, one bad job can mess up a lot of things because HD Insight doesn't have a notion of a resource pool or resource governance that's fully baked that would isolate one workload from another. So we're able to make progress on critical workloads, and other workloads we sometimes will schedule them at a lower priority or a lower frequency so that they have less of an impact on the system. But we often will find that someone deploys a new workflow, maybe that engineer hasn't done this before, and they write something that's not particularly optimized, and that actually can slow down the whole system. We'll usually not alert until things are a few hours behind. We don't need it to be exactly up to date for daily reporting. We don't use this for alerting. But we will instead go figure out how to make this system alert after 2 or 3 hours that things are not making progress so that someone can go figure out what's happening and fix it. Usually it's job's not tuned. Sometimes as we add more nodes into the cluster because we've grown things enough that we're hitting some limit. That's the typical answer. Does that answer your question? Okay. Yes, sir. Oh, are we using analysis services cubes? I should clarify, this is the SQL Azure team. So we're the relational database team, and we can use cubes, and we use Power View and various things, but for the main set of reports, we're running reporting services directly off of this database. Yeah. Now, that's not that you have to do it that way. I will make a comment. This may not seem obvious to everyone in the room. When you work on a relational database engine and you want to motivate your team to make your relational database engine better, one way to do that is to make sure that it's the thing that gets stressed. So often, we'll create things that don't make any sense at all at first because we know the technology doesn't do it, and then we'll force the engineers to suffer until they actually go figure out how to make it better so that we can eventually sell it to you guys. That may sound a little backwards, but it actually is a highly effective technique. So what I do is I'll take information. If I want to go start spelunking through the data, I'll go pull up Excel and start running Power Pivot, Power View on top of that, and I'll pull in enough data to go say, okay, for this set of customer data, I might look at it over some period of time, and I'll look at 4 or 5 different things, and I'll set all that up. And I will do it, but there's no automation interface on it, so it's actually a bit of a pain. And I don't do it in a systematic fashion across the whole system, because for me, I actually value being able to automate it far more than anything else. At this scale, I can't have something fail, and I need to be able to do it in a form that's slightly beyond the average information worker. I mean, I've got a petabyte of data here, right? No matter what I do, a petabyte of data is a big problem. So, and it's growing. Like every day it gets bigger. So this is a good problem to have. It's also a bad problem to have. And we're constantly working with our friends in the BI team to make sure that the next version of their technology works fine. But the challenge I'll tell you is often to get that to work here, there's 4 or 5 things that are running pre-release software if we get to the point where we've done all of that. So you have to have a new version of Office, running a new version of the BI stack, and having that work with a not yet released version of SQL Server. And that can be a challenge for making the system run. So to get the reports to run so that the VPs can see what they need to, we'll usually cut down the number of degrees of variables that run in the automated form so that we can get that to work right. So this is a bit more about how the sausage gets made here rather than necessarily what you should do. If you're running released bits of all of these technologies, we have a lot of customers that are very happy running cubes and running their reports off of that, and that's great. Most of the skill set that we have in the core engine team is not really heavy on DAX or MDX, and as a result, running relational queries is actually easier for us. I'm the QP guy, right? I like to write queries in SQL. DAX, to me, it's pig Latin. Oh, was there a question? I'm sorry. I apologize, I didn't see you. I'm sorry, you're gonna have to speak a little bit louder. There's a fan here. Yes. Right. Okay, so the question is, how are you doing it? Are you setting things up and going to one region, or are you running stuff in distributed form across the world for your Hadoop cluster? So you guys can see here in this diagram, in this particular configuration, we're running the Hadoop cluster in one region, and we're pulling all the data from around the world into that region to process it. It's not the best thing at scale because you eventually want to have Hadoop regions in each area to pre-aggregate, but when we built this, we just had one Hadoop region, and often we're running at scales that are big enough that we have to negotiate with the capacity guys for Windows Azure to get enough machines to do this, and it's easier to do that in one region than every region because we don't want to steal stuff from customers. Often we can run in data centers that are not yet open for you guys, and as a result, we can get capacity that you guys would otherwise not be able to buy. Does that make sense? So yeah, there's a lot of details in terms of how Azure runs our service, and some of those influence the choices here. So it's not that it's right or wrong to do this. If I were to do this today, I would build aggregation capabilities in each region locally, and then I'd pull whatever aggregated results I want into a central region to do my data warehousing. And that would probably be a more sane model, but fixing a system like this that has to run 24/7, once you've got it running, is actually much harder than starting it off with a fully distributed fashion. There was not the ability to do HD Insight in every single region when we first started this, which influenced that decision as well. Did that answer your question? I'm sorry, say it again, please. This is HD Insight, Hadoop on Azure. It's using the Hortonworks distribution that we've gone and extended. It's the exact same thing that you would be able to go do if you go into Azure and you click on that. Now, I will tell you that there's some pieces of the system here that I haven't really spelled out, where we're running components that are custom things that we built inside of Microsoft. And some of those things are technologies that will eventually go out in the world, and other things are just things that are going to go away and get replaced by something else because they were scaffolding. So the scheduling piece, for example, is not the same as what you would do because we had a different scheduling piece at the time. But there are open source and public scheduling technologies you can build to do this, and it's not that hard to build your own if you wanted to do that. So I'm showing you the logical conceptual diagram of this. There's a few details about how does the queue work. We have our own component over here to do ETL. That was all custom code. So these pieces are things that we built. You could do the same thing with SSIS packages or whatever technology you wanted. We just happened to make some choices at the time. Sometimes those choices were made for good reason. Other times they were not. So I don't mean to suggest more than the conceptual picture here. Use a scale-out technology like HD Insight that can do map-reduce jobs, figure out how to write pig scripts or Hive, and then do aggregation there as a precursor to doing ETL so that you can get things pre-aggregated and then insert into a single large data warehouse. Now, not everyone at our company does it exactly this way. We are very heavy on doing the data warehousing because we build data warehouses. That seems like a really good idea for us. Some other guys do not do that, and I will say that the amount of insight they can get in their service is substantially less than what we can do in ours. So often we can go figure out what's going on and do reports on a level that people who aren't using these technologies are having a hard time doing. There are trade-offs here, though. You have to pick what's your expertise, what's your interest, where do you want to focus. We want to make sure that we're growing the databases and the capabilities of the databases to do more and more of that. And over time, we're looking at, can we run some of these data warehouse technologies in the cloud? And so there's lots of stuff that we're working on in the future for how do we continue to democratize this technology and make it more turnkey so the average customer can click a few buttons and have something like this so they can build their own cloud service. Are there any other questions? Okay. So some of this we've talked about here. Hadoop or similar is the general technology we're using to do aggregation. And aggregation or trace analysis are really the only two main things that I think you have to think about here. So if I have a login sequence, first you hit this node, then you hit this node, then you check this, and then eventually you get done. This sequence, you're often checking these to see, do I see all of these in the right order, or do I not see them in that order? How often am I getting success? How often am I getting failure? At what point am I failing during that sequence of steps? That's the trace analysis path. And then the aggregation path would be number of logins that succeeded versus number of logins that failed. And these become very, very simple queries if you think about them in SQL terms. But in terms of how you have to write them here to get them to work at scale, you have to think through, okay, how do I write the map job? How do I write the reduce job? How do I figure out how to write the right number of mappers and reducers? And what's the configuration file for Hadoop? These are not native skills for average SQL Server guys, but they are not dissimilar to the types of stuff you already know. You just have to go figure out how to make it work, run it, use that as your ETL pipe to get pre-aggregation at a scale-out form, and then the results can be imported using regular tools. The telemetry, in terms of consuming it, we run reporting services on it, we run ad hoc queries against it, we use all the normal stuff you do in a big scale-up data warehouse. We run queries that are just data warehouse queries, and as I mentioned, we're doing partitioning, we're doing clustered column stores, we're running regular fact star join queries, and that tends to work really, really well for a lot of the stuff we want to look at every single day. Now, this can be scaled by a couple of different factors. If you've got enough money, you can buy more cores for Hadoop and keep scaling out your aggregation there. You can buy a bigger data warehouse box, or you can change the grain in which you're aggregating from 5 minutes to an hour or something so that you can have less data pumping into different parts of your system. And the nice part about this is you're getting to the point where you finally are able to deal with the small knobs that can allow you to tune your system so that you can keep growing that system so that if you don't have hardware right now or it's going to take 2 months to be able to get more machines, then you can still adjust and keep running your business at a small enough level of change so that the whole system doesn't just hit a brick wall and fall over. The challenges with this kind of approach are latency. And then the other comment that I'll make is that Hadoop is a very different beast. It's not part of the Microsoft tools ecosystem, so you have to really go figure out how much you want to go translate things back and forth. Often you're writing things to text files and then translating them in and out of the Microsoft ecosystem back into some Java-based ecosystem. Okay, so I'm done talking about batch pipelines. I'm going to start talking about alerting pipelines now. And alerting pipelines are nice because these are a little closer to what you might expect to a traditional SQL environment, more like a streaming query. And there's a bunch of stuff you can do here which actually is really, really cool once you build a streaming pipeline. The part that I like about it is that at first you think, okay, I get data quickly, I can fire some alert. So I'd like to walk you through the mental model for how you start building alerting engines and then work to what does that mean over time. So the first thing you typically do after you get this up is say, okay, if I have more than 5 login failures in a minute, then I should fire an alert. And so you build this, check it in, you let it run for a while, it's not happening all the time. Then all of a sudden, a lot of people start using your service, right? Maybe you have 5 times the users you had before. And then one day someone has something they check in who's using your service and they just have a login thing that's failing all the time. And it's their problem. They have a bad password or something like that. And then the alert starts going off. And then every day, the alert starts going off more and more frequently because the limit of 5 was just checked in as some random number, and you have no idea what the number actually should be because it's just a fixed number and it doesn't scale as your service scales. So getting to the point where you can deal with getting alerts to work correctly and not actually having to manually tune each one of these knobs is actually the biggest challenge in building one of these pipes. So if you do it right, you can eventually use technologies which will figure it out how to auto-adjust for you, and you won't have to actually wake up in the middle of the night because it won't be firing alerts unless it's really, really important. And I'll show you something at the end about what we do that's pretty cool. How many people have heard of event hubs? Event hubs is a new technology. Think of it as a sort of an in-memory service broker, like a message routing technology. BizTalk might be a better analogy. But you can route messages from place to place, and you can do so very, very quickly, and you can plug in different types of technology. So it's a message bus of some form, and you can also use it to get scale because it can, you can have a certain number of readers and writers, and this is in preview in Azure right now, and it's actually a very nice technology to basically build these alerting systems because they often can be written such that they don't ever touch a disk. And that means that you don't have to deal with throttling limits. As long as you don't need the durability of the messages, you can get them into your alerting system very, very quickly and then do stuff on them with low, low latency. So when we go look at customer calls to the SQL Azure service, we end up having this measurement that we keep track of, which is called time to detect and time to mitigate. And we actually measure for every single important incident exactly how long it was in minutes or seconds to be able to catch that issue. Like the customer's database went offline because 2 machines failed at the same time, and we didn't have a quorum to allow you to have a safe number of read replicas for your data. SQL Azure keeps multiple replicas always warm, and if a machine dies, there's automatic code to rebuild another copy of your database on another node without anyone ever getting called. But in the unlikely circumstances that there are correlated failures or failures that are just temporarily correlated and you get unlucky, then we have to do something about that. And we might have an alert to tell us, hey, there's a problem here. We might have lost too many nodes off of that customer's database and have to go fix it. So we want to figure out how to detect that as quickly as possible. We have automatic logic that tells us, that figures out if the database is not healthy, we actually block logins to it, and that way we can make sure that there aren't any writes happening on just one node until we get enough replicas rebuilt so that it's safe. And we also have copies of the backups and all sorts of other things that are happening during that time period. So there's layers and layers of stuff that we do so that we don't have any possibility or any significant possibility the database data can be lost. So in order to find out how to make that actually work, you have to go build the alerting system to tell you, oh, wait, this went down, and what we're going to do about it. Now, initially, we'll just say, OK, if you have one replica, fire an alert. That'll work great. But the thing you want to actually know is, what if a whole bunch of customers were on that same set of machines that died at the same time? You have to figure out how to get them all fixed. And if we have too many databases down, then we have to go through a more formal process to figure out what happened in our service and why did that happen. And if we had 100 customers unable to log into databases, even if none of them tried to log into the database, we actually go and have to answer to our vice presidents as to why that happened and figure out what we're going to do to make that better next time. So we have to figure out what code we're going to change and how we're going to make it so the amount of time that could possibly happen is increasingly less and less over time. I mentioned that we have an SLA for our database service, and the SLA used to be 3 nines for SQL Azure, and we moved it to 4 nines. And the way we did that was by following this process on taking alerts, doing RCAs on why things went wrong, and then going through and putting new fixes into the service so that it became less and less possible for some set of nodes to go down at the same time. That might mean we're more aggressive in terms of how we do backups. It might mean that we have more logic to be able to be careful about what happens when we're doing deployment of code, patches to the system, so that we can't have 2 nodes go down at the same time. All the normal cases of that are already handled, but sometimes there are esoteric things that can happen in the service, and since it's a big distributed system, and that sort of stuff is what we're trying to alert on. So we end up figuring out what's the smallest amount of data that we can capture to figure out whatever that key alert is, and we can then take that and track down, okay, this is the thing that we should have fixed, and someone needs to get woken up in the middle of the night to go manually press the button to fix that until we can get the code written to automatically do that for us. So we're constantly automating those various actions to do resolution of trouble until we get that to be automated fully. Okay. Oh. Is our alerting for human beings, or is it a mix of stuff for machines and human beings? I think that the evolution about how you should think about alerting systems is initially it's for human beings, and then you eventually get tired of the computer talking to you, and then you say, you know what, I really don't want to talk to you anymore, computer. Why don't we build a system that if you think about it, you have a piece of code that runs your service, right? And that main piece of code, you probably have to go through all this testing and validation before you can change. And it may mean that you can only push out changes to that every week or some frequency. But it's not like you can just go change something and check it in and expect that the whole system's going to work. You have some process defined in that piece of code. And the bigger the piece of code, the more likely you have more and more process defined on it after a while. So what you end up doing is you build an external alerting system that tries doing stuff. And that alerting system is a smaller piece of code. And then you get to the point where, you know what, if it's alerting all the time and it's very, very frequent, maybe there's always a certain fix that you try that works 95% of the time. It doesn't even have to work all the time. Maybe you reboot the node, just to pick something, right? If this certain condition happens, just reboot it. Hit it with your hand, right? Like the Apple thing. And we've built systems that initially will say, take the alerts and automatically run the repair action. And then if that doesn't work, then alert. And so then you start building more and more of these systems to sort of figure out how to capture what were the problems that were happening, what's the most likely way to mitigate as quickly as possible. And then you have a queue of these things that the engineers will go look at during the day to figure out what the root cause was, and then figure out how to make it so it's less likely that you have the alert in the first place, or if you have the alert, you can have the ability to get higher percentage of the corrective action working. And these are the techniques that you just iterate on. You have an engineering team that just actually looks at how many alerts did I have and how bad were they, and that's their work for the day. That's all they do now. And once you get that fully baked and you don't have any more, then you can add new features. Does that make sense? Okay. Okay, so now we get to the fun part. So once you have a telemetry system that's running, the thing you realize is, I don't know how many alerts I should be having in an hour. Maybe it should be 0. Maybe it should be 1 million. Somewhere in between would probably be good for whatever random thing you want to alert on. But if you use machine learning algorithms, you can have the system figure it out for you. So we end up figuring out that I don't want to know if there's 5 login failures. It's not useful for me anymore, because I probably do have someone that checks in a piece of code. 5 login failures is happening all the time for them. And on some clusters, it's 1 number. On other clusters, it's another number based on how many people are on that service. So it would be really, really cool if you could get the alerts to auto-tune themselves. You just want to learn, well, the average number of alerts is something like this. Why don't I just have the system figure that out for me? And then I only want you to call me if it's really, really off. Because I've got a system that's already, rebooting the machine every once in a while if something's going wrong. Now what I want to do is figure out, is something strange happening? I only want to bug someone if something really strange is happening. If I have alerts that are just expected at this point, fine. But if I have something that's really out of the ordinary, I really want to know about that. Because that's the time when I want to have a human go work on that problem. It'll probably be a fun problem too. So let's talk about that. We actually use a lot of the algorithms that they use in the Azure machine learning service, the Azure ML. But we also have our own custom versions of these built to track down certain kinds of errors. And these are things that you guys can do. I know machine learning sounds like space age stuff, but really at the end of the day, there's a lot of really basic algorithms that anyone can run if you know how to do averages. That's pretty much what you're doing, right? Machine learning could just be called how to figure out averages automatically. There's a lot more than that, but for a lot of the basic stuff, you can get great value out of a very, very simple amount of math. Okay, there's two main approaches for how to build a machine learning system to do alerting. Option one, you go get R. R is free. You can download it. You can run whatever you want in it. It's great. There's a bunch of algorithms. You can download them off the net, and you can do things like moving average windows and things like that. You can also try the Azure ML service, and they demoed that in the keynote, and that's getting better and better. It's still pretty new, though, and it does some limitations in scale. Probably would not affect you guys as much as it affects me, since I'm running things at very, very large scales. But overall, the idea is both of these things are trying to make machine learning algorithms easier for anyone to do. You don't have to be an expert. You don't have to be a data scientist. At least you don't have to immediately be a data scientist to get value out of this. There are cases where you do want to go be really smart with data science algorithms and figure out how you can use machine learning the right way. So if you want to predict how often people are going to click on a credit card score or something like that, you can use machine learning algorithms for that as well. But those are far more complicated. A lot of times if you just want to keep your database services up, then all you need to do is figure out, am I seeing an unnatural number of errors right now? And you can have the system figure out what the word unnatural means, and then use that to determine whether I should alert or not. We used to do static alerts, and now we pretty much just do alerts that are machine learning algorithms because they're able to detect stuff faster than any other technique that we've been able to come up with. So I'm going to show you an example of this. So let's say that I wanted to track user errors, and I wanted to know about spikes in user errors. I don't have any idea what the errors are. I don't even care. All I want to know is, are there lots and lots of errors that are far different than normal? And if I have a deviation from whatever the normal operation is, then I want to fire an alert on that. Sometimes it's a false alarm and I shouldn't do anything. Other times it means that the whole server farm's on fire, and that's really, really bad. So you don't necessarily have to care what it is. You just want to know, should a human be looking at it or not? And machine learning algorithms are both smart and dumb at the same time. They can mostly tell you, should a human look at this problem? So in this particular example, you can see here that we have, over time, certain number of errors that are happening. And over the course of a couple of hours, all of a sudden, things started going really, really badly, of course, in the middle of the night, as always. And at some point, the blue line up here is a threshold where we decide we're going to alert above that threshold. And we have a machine learning algorithm that figures out what that threshold is. Effectively, all it has to do is say, you know what? I want to take the 90th percentile frequency for the errors, and I want to measure that over a couple of days or a week. And then I want to have you tell me, do I ever cross the 90th percentile threshold for whatever it was I was looking at? So maybe that means 3 errors at a time, average 3 errors over an hour is too high. And then once you hit that threshold, you'll see that little red dot up there. That's saying the system said, you know what, that's bad, maybe. Let's have someone take a look at that. And this way, you only call people in the middle of the night when things are potentially far, far worse than average. So if you're OK with the 90th percentile number and below, then all you have to do is have it can figure out how many errors are normally happening, and then watch for cases where it's far off from that. It's that simple. We now catch errors before most people ever call, because we can do this on whatever system, whatever thing we want to watch. You can watch anything. You can watch sales per hour. You can watch errors per hour. Anything you can measure with telemetry, you can now start doing these algorithms on. And that's the great part about it. They are smart and dumb. They'll sit there all day and tell you when things change without having the slightest idea what it is they're watching. And that's a really cool, powerful feature, because once you do that, over time, let's assume that the service becomes more and more busy, and the average noise for how many errors are there starts to creep up. That threshold will go up over time, because the average number will also be higher. And you're not going to have a bunch of time where you have false alarms all the time, where you get woken up at 2 in the morning to go figure out why the service is down, only to find out that someone just has a piece of code that didn't update their password, and all of a sudden it's failing, and you're getting an alert instead. The frustration that you can see in my voice is not because this hasn't happened to me. This happened to me all the time, right? You hate this once it happens. And you listen to someone tell you you have to wake up in the middle of the night and go do some paperwork over these kinds of things because someone has a bug in their stuff and they didn't update their alert properly. Those are the worst things to happen. What happens for us is we get to be on call for some period of time, usually a week at a time, and whenever real errors come in, it's fine, right? Whether that happens during the day or the night. But when a false alarm comes in the middle of the night, I just go livid. I get really, really angry and start yelling at people. And this is one way to minimize the number of times you get called in the middle of the night with that. So if you're running a 24/7 web service, I suggest you invest in one of these things. I have one more example to show you. This one's a bit more complicated, and I need to explain what was happening. Inside of our service in SQL Azure, we can roll out code all the time, and we are rolling out code all the time. So we have a piece of code that was generating too much telemetry, and this was causing us to get throttled when we were trying to write out to the storage account. So we needed to figure out how to cut back the amount of telemetry on that one component so that the whole system would work cleanly. And what ended up happening was we checked in the fix, and we rolled it out, and all of a sudden, the system alerted. It goes, whoa, whoa, whoa. There's far less telemetry. You might have had a system break and no telemetry is coming out, or some major piece of telemetry is missing. So this turned out to be a false alarm, but it was actually a really good false alarm, because what was happening is it was reteaching itself that you've got far less telemetry now, and now I need to actually get a tighter bound because you fixed this bug. So we just saw the alert and we go, okay, yes, we've rolled out the code, we know it's good, false alarm, go back to bed. Now, that's not the best thing in the world, but it gives you an example about how this system can be used to say the absence of telemetry is also something that can be alerted on. And we use that as well because if you have no heartbeat coming out of your cluster, that could mean that everything's dead. And then all of your alerts don't work as well. So we have alerts set up for that to check for it. And this is how you end up running these cloud services at scale. So you can see the amount of data that we were writing out, and we have lots and lots of data here on the number of nodes, and all the reds there are where we were alerting. And you can see right before that was when we still had data up there, but those weren't alerts. Only after the data dropped down and came back up did we start actually alerting, and then you can see how it got back into a very normal pattern down here. That's much closer to what we were expecting to see. So we're dumping out information every so often from each of the components, and maybe every 5 minutes or whatever, they might output some information from a DMV, and that information will show up as a little tiny spike there, but this is the range that we're looking for, and that's much, much better than what was happening over here. Are there any questions on this one? No? Okay. I believe that gets me to the end of my talk. So this is how we run the SQL Azure service. If you guys have any questions, I'll be happy to answer them. Thank you for coming.